Welcome back. In this concept development practice page, we're going to be looking at the concept of inertia. And the first person to come up with this and write about it was Galileo back in early 1600, 1605 or 10 in Italy. And I think all of us have experienced this. For instance, if you want to go up and push a little kid, you can push him down. But if you go up and push a big kid, it's way harder to push down, okay? Likewise, if you want to catch a small ball, okay, it's coming at you, it may be easier to catch than, say, if someone was throwing a truck at you, okay? Because once an object is in motion, the bigger it is, the harder it is to stop that motion. And once it's stopped, the harder it is to start that motion. So it's easier to throw a baseball than it is to throw a bowling ball. Not because of anything except its mass. The more mass that it has, the harder it is to get going. But once it's going, the harder it is to stop it. Okay? So this is the idea that Galileo faced, and this is called inertia. It's also the first law of Isaac Newton, who stole it directly from Galileo, and it's one of his laws of motion also. So I've mentioned this in class a couple times. An astronaut in outer space away from a gravitational or frictional forces throws a rock. The rock will what? What will happen to the rock? Okay. Make an answer. Okay. The rock will continue moving in a straight line at a constant speed forever until acted upon by another force. Consequently, the astronaut also will move. The rock's inertia is going to put a force on the astronaut, just like the astronaut's inertia is putting a force on the rock. So that's pretty cool if you've ever done that with ice skates, two people pushing each other. The little guy will go far and the bigger guy will go a little distance, but they'll both move. Okay. The rock's tendency to do this, going in a straight line at a constant speed, so once it's in motion, it stays in motion at a constant speed in a straight line, that's called inertia. Okay, that's its inertia. Okay. Now, this is a really interesting question. A lot of people miss this. See if you are one that's going to miss it or get it right. If I take a string and tie a weight to it and sling that weight, so I put a ball on a string and sling it around and around and around and around and around in a circle, and the string breaks, okay? So it's going around in this circle going this way, and the string breaks. Which way does the ball go? Does it continue going in the circle that it was in because it was used to going in that circle, and so it's going to keep going in that circle? If so, I want you to pick D. If you think that it's just going to go in a straight line tangent to the circle, then I want you to pick C. Or since it's trying to get away from my hand and the string breaks, it's going to go away from my hand towards B, some kind of intermediate between straight line and being slung off. Or do you think it's just going to go straight out away from my hand, away from the arc of the circle? If so, pick A. What do you think will happen? The answer is C. It's going to go in a straight line because it has a, once you stop putting a force, like if that string were to break, there's no longer any force. There's a force of tension on that string. But if the string breaks, that force of tension goes to zero, and that rock gets thrown just like the astronaut threw it. It's going to go in a straight line in the same direction that it was thrown. So what's its direction when the string breaks? It's going this way. Okay, at the moment that string broke, it's going this way, and so it's going to still going this way, and it's going to continue this way straight out forever in the same direction. Okay. All right, we have a new scenario. Suppose you're standing in the aisle of a bus that travels along a straight road at 100 kilometers per hour. You hold a pencil still. Okay, so he's got a pencil above his head. Above your head, then relative to the bus, the velocity of the pencil is 0 kilometers per hour. Okay, so it's not going any faster than the bus is. The pencil's going 100 kilometers an hour, the bus is going 100 kilometers an hour, you are going 100 kilometers an hour, everything, the seats are, everything's going the same. So what's going to happen, okay, relative to the road, the pencil has a horizontal velocity of what? Okay, so relative to the bus, it's not moving. But relative to the road, let's imagine that it was an invisible bus and you were invisible and the seats were invisible, but the pencil was not invisible. Someone along the side of the road would see a pencil coming down the road at what speed? Less than 100, 100, more than 100. Okay, relative to the road, it's traveling at 100 kilometers per second. Okay, so that pencil is moving fast. So here's the next question. Suppose you release the pencil, so you're going to drop it. While it's dropping, relative to the road, the pencil still has a horizontal velocity of what? Relative to the road, it still has 100 kilometers per hour, just like it did a second ago. Okay, but you're dropping it, and while it's dropping, it's still moving forward at 100 kilometers per minute or per hour. This means that the pencil will strike the floor where? Okay, will the pencil go forward and strike the floor way in front of you? Will it be directly below where you dropped it at your feet, or is it going to fall behind you? That's a good question. Think about it before you answer. It's going to fall at your feet. So for instance, if you are sitting in that seat and you throw a quarter up into the air, it'll fall back down into your hand. It's not going to fall into the seat in front of you, and it's not going to fall into the seat behind you, even though that quarter is moving forward at the same speed of the bus. Because you and the quarter and the bus and the floor and the seats are all moving at the same, and so it is independent, all of that moving, and so it is going to move independently. So its downward motion is going to move independently of its forward motion. That is pretty cool, and that's a lot of people would miss this. Okay, so relative to you, the way the pencil drops is the same as if it were at rest. Okay, the pencil drops exactly like it weren't moving. Because if you think about it, your room is on the earth, and the earth is going 1,000 miles an hour around its axis, and the earth is moving around the sun at some ridiculous speed, as it takes an enormous path around the sun in 1 year. So even though everything is moving at tremendous speeds, if you were to drop your pencil on the floor, it would fall on the floor right in front of your feet, the same as if it were not moving at all. Okay, so how does this example illustrate the law of inertia? Okay, a body in motion tends to stay in motion unless there's another force acting upon it. Okay, so since the forward speed and the downward speed are independent of each other, the only force acting upon that is its force of gravity, and so it's going to go directly down towards the ground. Okay, all right. I hope you. I'd like you to put this in the box, please. I hope you understood. Thank you.